Hello, welcome. And today's topic we are going to study about the Fourier series. Okay, let us start with the function and the coefficients for this. In 1822, J.B. Fourier published a very useful theorem by which any complex periodic function can be analyzed. The theorem states that any complex periodic piecewise continuous function fx may be expressed as a series of sines and cosines in the form, which is the form of the function which we are going to write is fx equals to a0 plus summation of n equals to 1 to infinite a n cos nx plus n equals to 1 to infinite p n sin nx. Okay, the function fx is said to be piecewise if it satisfied the two well-known conditions. What are the conditions? First condition is the function must have finite number of maxima and minima. Second is the function must have a finite number of finite discontinuities in a period of one oscillation. Okay, the two conditions are sufficient but not necessary. In most of the physical problems, these conditions are satisfied. However, there are some functions which do not satisfy the conditions but may be expressed in the form of Fourier expansion. The function sin nx and cos nx for integral n are periodic having a period 2 pi in the interval minus pi to pi. Okay, since we know sin n x plus 2 pi equals to sin nx and cos n x plus 2 pi equals to cos x, so we can see the function fx represented by equation 1 from this equation above equation is periodic having a period 2 pi in the interval minus pi to pi. Okay, now we will evaluate the coefficient of Fourier series. What are the coefficients? A0, An and Bn. For this, we use the orthogonal property of the sine and cosine functions. Okay, what is the property? Integration between over the limit minus pi to plus pi sine mx cos nx dx equals to 0. Okay, or we can say integration over minus pi to plus pi sine mx sine nx dx equals to minus pi to plus pi limit cos mx cos nx dx equals to pi del mn. Here del mn is Dirac delta function and the value of this is 0 for m not equal to n and pi for m equal to n. So this is the orthogonal, this is the property which we are going to use. First, we will evaluate the coefficient a0. For this, we integrate equation 1 between the limit minus pi to plus pi. Equation 1 means our equation which we have written fx equals to a0 plus an plus bn in the form. So, now on integrating equation 1, we can write the equation minus pi to plus pi the limit fx dx, this is our LHS, equals to a0, putting the value minus pi to plus pi integration dx plus in the second term summation of n equals to 1 to infinite. Here this is the value n equals to 1, n equals to 1 to infinite. An minus pi to plus pi cos nx dx plus bn minus pi to plus pi sin nx dx. Since we know all integrals in the above equation will be 0, only first term will have the value of 2 pi. So we get a0 equals to 1 upon 2 pi minus pi to plus pi limit fx dx. Okay, this is the value of our coefficient a0. Okay, similarly we evaluate the coefficient of an and bn. So first, to evaluate coefficient an, we multiply the both side of equation. Which equation one? Fx, which we have written in first slide. We multiply both side of the equation by cos mx and integrate between the limits minus pi to plus pi. So what we will write? This we can write this by multiplying the equation in the both side by cos mx and rewritten with having the integration between the limit minus pi to plus pi. We can write the equation fx equals to cos mx dx equals to a0 minus pi to plus pi limit cos mx dx plus n equals to 1 to infinite an minus pi to plus pi cos mx cos nx dx. This is our second term in RHS. Similarly, our third term in RHS we can write plus n equals to 1 to infinite bn minus pi to plus pi integration limit cos mx sin nx dx. Okay, by using the properties which we have written in the equation 2 and 3, we have first term will be a 0, third term will also be 0 because m is not equal to n here also. And in the second term, here this in third term we have cos mx and sin nx, so we have this term will be 0. But in second term we can write a n pi del mn. Here del is the Dirac delta function, which the value of which is 0 when m not equal to n, and the value of which is equal to 1 when we have m equals to n. So we can write a n pi del mn, and when we put the m equals to n, we get a n pi. We have the value of coefficient a n equals to 1 upon pi minus pi to pi integration limit fx cos m x dx. Here in this equation we have put m equals to n, so we write here a m equals to 1 upon pi minus pi to pi fx cos mx dx. Replacing m by n, we get a n equals to 1 upon pi minus pi to pi fx cos nx dx. This is our coefficient a n. Now to evaluate the coefficient bn, we have evaluated both the coefficients as 0 and n. Now we will evaluate the coefficient bn. So for this we multiply both side of the equation 1, which is our equation 1 is fx equals to a0 plus an summation of an equals to 1 to infinity an cos nx plus summation of 1 to n equals to 1 to infinity bn sin nx. Okay, so multiply this equation by sin mx and integrating this between the limits minus pi to pi, we can write the equation minus pi to plus pi fx sin mx dx equals to a0 minus pi to plus pi sin mx dx plus n equals to 1 to infinite an minus pi to plus pi sin mx cos nx dx. Here dx is term is missing, but dx we can write here plus n equals to 1 to infinite bn minus pi to plus pi sin mx sin nx dx. By using the equations which we have written in the above section, we can write the value of the coefficients. We have only the third term, which is sin mx nx, which have the value bn pi del mn. So we can write when putting m equals to n, fx sin mx dx equals to bm dot pi. So we get bm equals to 1 upon pi minus pi 2 plus pi fx sin mx dx. By replacing m by n, we get bn equals to 1 upon pi minus pi 2 pi fx sin nx dx. So now we can write the function value fx equals to a0 plus n equals to 1 to infinite a n cos nx plus n equals to 1 to infinite b n sin nx. So the value of the coefficients are these: a0 equals to 1 upon 2 pi minus pi to pi fx dx, a n equals to 1 upon pi minus pi 2 plus pi fx cos nx dx, b n equals to 1 upon pi minus pi 2 plus pi fx sin nx dx. Okay. Now we consider the following two particular cases. What are the cases? First case is this: when the function is an even function of x, means f x equals to f minus x. The meaning of even function is when we put the value of minus x in place of x, then we get the function unchanged, means f x equals to f minus x. Then we have a0 equals to 1 upon 2 pi minus pi 2 pi fx dx. Okay, we can write this in the term 1 upon pi 0 to pi fx dx. And for the an, we can write 2 upon pi 0 to pi fx cos nx dx. And for bn, we can write 1 upon pi minus pi to plus pi fx sin nx dx equals to 0. This is the term for the function to be even. Therefore, for even function fx, we can write the function fx equals to a0 plus an cos nx, where the value of coefficient bn is 0 for an even function. So the value of a0 equals to 1 upon pi 0 to pi fx dx, and the value of an equals to 2 upon pi 0 to pi fx cos nx dx. Now equation this 7.5 represent the function fx in a series of cosines and is therefore known as cosine series in the interval 0 to pi. Okay. Now the second case is this: when function fx is an odd function, means if we put the value of x minus x in place of x, then we get the function is fx equals to f minus x equals to minus fx. Then the function is called odd function. For this function, the value of the coefficients a0 an are 0, and we have only the value of the function bn equals to 2 upon pi 0 to pi fx sin nx dx. So for an odd function of fx, we have the equation fx equals to n equals to infinite bn sin nx, where bn has the value of this. Above equation represent the function fx in a series of sines. So we can say this is sine series in the interval 0 to pi. Okay. Thank you.